Now I'd like to turn it over to Uday, our application engineer, who's going to give you a demonstration of VisualMILL for SolidWorks.
Thank you, Jerry. Good morning, good afternoon, or good evening to folks wherever you joined us for the webinar today. I will be giving you a presentation of VisualMILL in SolidWorks. VisualMILL for SolidWorks is an add-in, works in SolidWorks versions 2008 through 2012. It runs in both 32 and 64-bit platforms of SolidWorks. Upon loading a part document in SolidWorks, VisualMILL appears right in the menu bar, right next to the Tools menu in SolidWorks, which provides you access to the Machining Operations browser, the Tools browser, the Help Files, Getting Started Guide for VisualMILL. VisualMILL also has an entry right next to the Command Manager in SolidWorks, where users can quickly access the Tool browser, the Machining browser within SolidWorks. Users can switch from the Feature Manager design tree to SolidWorks VisualMILL from the Feature Manager tab by just clicking one poke of a button. The Machining Operations browser has primarily three tabs: Setup, Create, and Simulate. And the workflow would be going from left to right as you work through these tabs. Right under the Machining browser, we have the Cutting Tool browser, which allows the user to manage tools. Users can define several different types of standard tools. We support ball and mills, flatten mills, corner radius, engraving tools, chamfer, taper tools, thread mill, face mill, drill, center drill, reamer, tap, bore, and reverse bore. VisualMILL also supports dovetail, lollipop, and user-defined tools or form tools for programming toolpaths. The tool browser allows management of cutting tools. Users could either define tools or load tools from a library or select certain set of tools from a predefined library. For this part, we're going to be programming in the demo. I'm going to be loading two tools, a 1/4-inch and an 1/8-inch flatten mill. The Setup tab allows the user to define the machine definition, where the users can choose from a variety of machining methods. VisualMILL supports right from 2.5-axis milling, 3-axis, 4, and index 5-axis programming. Parts which are typically prismatic can be programmed using a combination of 2.5 and 3-axis methods. For this example, we're going to set the machine type to 3-axis. We will then select the post processor. VisualMILL includes an extensive library of posts where the user could select the post processor from the list of posts. The post can also be edited and customized by selecting the Edit button, and the post generator allows configuration of the posts. Newer posts can also be added to the existing library by creating new posts and saving them to the current library of posts. We will select the current post processor to host and specify the output file extension as .nc. In the next step, we will define our stock geometry. The stock materials could be defined as a box stock, where VisualMILL automatically determines the model bounding box to compute the minimum stock dimensions required to program the part. We'll change the length, width, and the height of the stock material, and the stock visibility can be turned on to display the stock model in SolidWorks. We will now go ahead and align part and stock to have the part aligned, the stock aligned to the part geometry. Using the setMCF operation, we will define the machining origin. The machining origin could either be selected by specifying a location on the part, or it could be set to the stock material. We could set it to the top face of the block, which would be the highest Z, and I'm going to choose the southwest corner for the machining origin. The workflow would be going from left to right. Once we are done through the setup process, we will switch over to the Create tab where we could define the milling operations. Under the 2.5 axis methods, VisualMILL offers facing, pocketing, profiling, remachining, V-carve roughing and finishing, engraving, chamfering, hole pocketing, and thread milling. VisualMILL offers a wide range of 3-axis toolpath methods, ranging from roughing, re-roughing, pre-finishing, finishing, remachining toolpath methods. The 4-axis methods includes both indexed and continuous 4-axis milling. The indexed operations are typically performed using a table rotate operation, and any of the 2.5 or 3-axis operation could be applied towards an indexed 4-axis machining. The continuous 4-axis methods include facing, pocketing, profiling, 4-axis roughing, finishing, engraving. The hole machining methods, drilling, tapping, boring, and reverse boring are also included. We will now try to program the pockets using a 2.5 axis pocketing. We will select curves as machining regions and select the features to program. From the Tool tab, we will use a 1/4-inch end mill. We'll switch over to the Feeds and Speeds tab to load the feeds and speeds. Can be loaded from the tool or can be selected from a table depending on the material properties, the tool material. Based on the tool diameter and the surface speed, VisualMILL computes recommended feeds and speeds. The clearance parameters can be set under the Clearance tab. The cutting parameters allows the user to specify the tolerance, stop to leave, specify a cut pattern from either offset, linear, spiral, or radial cuts. The cut direction can be set to climb, conventional, or mixed. The step distances can be specified under step over control. The cut levels allows the user to determine the depth of cut. The depth of cut can be automatically detected from the model by selecting the floor of the pocket. The depth per cut parameters can also be controlled so that the pocket feature can be programmed in multiple steps. The Entry and Exit tab allows the user to define the approach, engage, retract, and departure motions. And the parameters for the approach, engage, and retract departure motions can be set right under the Entry and Exit tab. Selecting Generate would process the toolpath. The toolpath is now visible. Selecting toolpath visibility turns the display of the toolpath on and off, and the toolpath display in levels displays the toolpath for each level of cut on the model. We will now switch over to the Simulate tab to run the verification of the toolpath. Select the machining operation and hit Simulate. Runs the material removal simulation. Users could go back and edit the operation by selecting the machining folder, double-click to make changes. You can edit the tool, the cutting parameters, the feeds and speeds, and just hit Generate to recompute the toolpath. To machine the whole feature, we will now make a copy of this operation by selecting the operation, right mouse click copy, and paste. So the current set of operation is copied over. We'll edit the operation and select the features to machine. We're now going to click Generate to process the toolpath. So by creating an operation and making a copy of it saves programming time for the end user in programming multiple features. We'll now create a profile toolpath to cut out the part from the piece of block by going to 2.5D milling and profiling. We'll select our machining features for profiling. Specify the tool, define the cutting parameters. We'll choose Determine using 3D model to automatically determine the direction of cut. The cut levels allows the user to detect the total depth of cut for the profile operation. and this can be picked directly off the 3D model. In selecting Generate, we'll process the toolpath. The toolpath is now visible. We'll run the simulation or the verification of the toolpaths. We'll now apply some design changes to the part in SolidWorks and see how this affects our toolpath. I'm going to edit some of the model features, modify the pocket, and as the features are modified, you will notice that the machining operations associated are automatically flagged, indicating that there has been a design change of the part in SolidWorks. So we could select the operation, right-click, and select Regenerate, would automatically update the toolpaths. And we can switch to the Simulate tab to run the verification. Selecting Simulate would simulate all the operations with the design changes. So working with an integrated CAM system reduces programming time when there is design changes and rework involved. We will now take a look at the estimated machining time for the entire set of operations by selecting Information under the Machining Operations set. This lists the machining operation time for each individual operations and provides a total estimated time for the entire part. VisualMILL also offers some documentation and reporting tools where you could prepare a setup sheet which can then be handed out to the machinist at the floor who can prepare the tools required to program this part. The setup sheet can also be customized by the end user. So the setup sheet also lists the tools being used for the current operation and lists out all the machining operations involved in this process. One of the nice features VisualMILL offers is the ability to save these machining operations into a knowledge base. We'll go over to the Create tab and select Save to Knowledge Base. This allows the users to reutilize the same operations across family of parts when you're trying to machine similar type of parts, which would reduce the programming time for the programmer. Once the toolpaths have been generated, we will generate a posted output file by selecting Post. VisualMILL automatically generates the NC file and previews the file in an NC editor. You can also run a backplot of the posted toolpath. We will now go ahead and reutilize the knowledge base on a part that is very similar to the one that we just programmed to see how we can reduce our programming time. The part that's currently being loaded has a boss feature on the model, which is slightly different from the part we just programmed. So I'm going to go over to the Setup tab, define my stock geometry, and I would go to the Create tab and load the knowledge base. As you notice, VisualMILL automatically brings in all the operations from the knowledge base. I would now edit an operation, select Curves as region, and select the features to machine, and selecting Generate would process the toolpath. We can also add additional operations. So I would like to create a facing toolpath around the boss. So I'm going to go ahead and select 2.5D milling, facing, specify machining features. I'm going to pick the island in here. I could also add new tools as I go along programming the parts. I'm going to create a 1/2 inch end mill, specify a tool number. From the roughing parameters, I can define my tolerances. And at the Cut Levels tab, I can determine the top of cut and specify the total cut depth by specifying the floor of the part. Selecting Generate would process the toolpath. The machining browser also allows the user to reorganize the sequence of operations by just a simple drag and drop. If you wish to delete any of your machining operations, you can just select the operation from the tree and hit delete to delete the current set of operation. We will now run the verification of the toolpath from the Simulate tab. Select the machining operation, and click Simulate, runs the verification. Now I'm going to run the simulation of the pocket operation. And once the toolpaths are ready, you can go back and post-process the output. Select right-click and Post will generate the posted output file. We will now take a look at a couple of examples which involve 3-axis programming